Okay, welcome back. Now, to continue, we can do some initial measurements that would tell us that one particle is in psi naught prime and one was in psi naught double prime. Yeah, so such a measurement, initial measurement would give us this information that one of the particle is in psi naught prime state and the other particle is psi naught double prime state. But we cannot distinguish the particle, that is, which particle is in psi naught prime state and which particle is in psi naught double prime state. So the only thing we can do about from the initial measurement or obtain from the initial measurement this would give us the information that one of the particle is in psi naught prime and the other particle in psi naught double prime. So, so we could say a measurement, let's say some initial measurement uh, gives information that one particle is in psi naught prime state and other one particle was in, rather इसको भी was कर लें, was in psi naught double prime state. Yeah. But what we would not know, but the measurement would not tell us which particle is in which state. Which particle is in which state. Yeah, so this is something which is basically the concept of particles being identical. This is because of the concept because that particles are identical. Say, so one cannot distinguish. So you can say, i.e., one cannot distinguish the particles. The particles, yeah. So the so the initial state could be sign. So from this one would say that we could conclude that from this we could conclude the initial state could be psi naught or psi naught bar. Yeah. So it could be either psi naught or psi naught bar or any linear combination of these two or any linear combination of psi naught and psi naught bar. Yeah. And so what we achieve from this, that there is some exchange degeneracy. Yeah. This uh, leads to the fact that there is some exchange uh, degeneracy. Yeah? So this is the concept of exchanging. So we underline this exchange degeneracy. So suppose we use some linear combinations that are symmetrical. and antisymmetrical as orthonormal basis. So from this concept, that is this concept of exchange degeneracy, we sort of develop two linear combinations. One linear combination would be a linear combination which is symmetrical, and the other linear combination would be an antisymmetrical linear combination. And these linear combinations are made up of orthonormal basis. Yeah. So let's say, suppose we use linear combination that are either that are not either that are symmetrical, or anti-symmetrical. Symmetrical as an orthonormal basis. Orthonormal basis. So what are those two bases? एक को हम कहेंगे साई नॉट, सुपरस्क्रिप्ट में ब्रैकेट में लिख देंगे एस. एस स्टैंड्स फॉर सिमेट्रिक. या एंड दिस वुड बी इक्वल्स टू 1 अपॉन under root 2. 1 upon under root 2 is the normalization factor. That is, we are talking about orthonormal basis. Yeah, so we normalize those bases by multiplying the linear combination by a factor of 1 upon under root 2. Yeah, times psi naught plus psi naught bar. Yeah, so this is one of the linear combination, and we could also think about the time dependent linear combination as well. So, and we could also write it and with time dependent combination जो होगा that would be something which is जिसको again psi bracket में s और यहाँ पर function of time लिखा जा सकता है. So we can also have a time dependent orthonormal basis, asymmetric basis, and there is another orthonormal basis which is antisymmetric जिसको हम a से जाहिर कर रहे हैं. And this antisymmetric basis is again equals to normalization factor 1 upon under root 2. But now the sign is minus. So remember हमने बात की थी कि antisymmetric states क्या होती हैं? ऐसी states that upon interchange of particles in those states, अगर साइन चेंज हो जाता है वेव फंक्शन का, सो इस सूरत में दोज आर एंटीसिमेट्रिक स्टेट. सो वन ऑफ द स्टेट इज साइन नॉट एंड द अदर वन इज साइन नॉट बार, एंड बीच में अगर माइनस साइन लगा हुआ है देन वी आर टॉकिंग अबाउट एन ऑर्थोनॉर्मल एंटीसिमेट्रिक बेसिस with a minus sign as a linear combination. Both are linear combination. And similarly, and with time dependent अगर होगा तो t dependent, देन उसको हम रिप्रेजेंट करेंगे ब्रैकेट a of time. Yeah, so this is basically two, in fact, states, two orthonormal bases. So our initial state is some arbitrary linear combination of these two. Yeah, so हमारी जो इनिशियल स्टेट हो जाएगी अगर हमारे पास दोनों पार्टिकल्स, दोनों तरह की इनफैक्ट ग्रुप ऑफ पार्टिकल्स मौजूद हैं, देन हमारी इनिशियल जो स्टेट होगी that would be some linear combination of these two orthonormal bases, that is the symmetric and antisymmetric. Yeah, so one would say uh, therefore therefore our initial state is some linear is some rather linear combination of these orthonormal basis. कैसे लिखेंगे? Where we could write it as, so capital psi. So capital psi से जाहिर करें, capital psi not, because we are talking about initial state. So let's say यहाँ पर मैं not लिख दूँ. So this capital psi not is basically a state with two particles whose distances are R1 and R2, and they are written as a linear combination of these two orthonormal bases. One of the orthonormal bases is symmetric and the other one is antisymmetric, and we could write it as alpha, some probability amplitude, describing the probability that of the antisymmetric state, plus beta, let's say, psi naught of S. So remember this alpha, these alpha and beta are the probability amplitudes, and these probability amplitude that give you the probability that the particles are in the antisymmetric state or the particles are in symmetric state, depending upon the type of the particle, remember. Yeah. And similarly, when one could write for the time dependent type or time dependent version with time dependency. You could write it the same state as psi capital में of t equals to alpha psi naught of a plus of t plus beta psi naught of s of t, function of time. So you could write them as a function as time dependent states as well. Yeah. So this is basically true also for the time dependent. So whatever we are doing is not only true for time independent state, but also true for time dependent state. That is why we are emphasizing about time. So we could think about the Schrödinger picture or the Heisenberg picture or the interaction picture. So the identical particle or many body quantum system, where we talk about many particles or many identical particles, then the treatment for placement of those identical particles in time independent state and in time dependent state is same. So both for both type of time dependent and time independent states, the same formalism or the same principles are used. Yeah. Okay, so that's why we are each time when we talk about a state, we also give its time-dependent version as well. So when we look at the probability to find a particle at some position, let's say उसको मैं position r prime कह दूं, and the other particle at a position r double prime, we need a squared wave function because that gives you the probability density. So what is probability density? You remember from lower classes, uh, probability probability density, that is probability of finding a particle somewhere is defined by squared wave function. Yeah, absolute squared wave function, squared wave function. Therefore, probability of finding one particle at some position r prime, at some position r prime, let's say, and the other particle, and the other particle at position r double prime is given by squared wave function. Yeah. And what is that? That squared wave function जिसको हम probability कह रहे हैं, probability that one of the particle is at r prime position and at the other particle is at r double prime position is given by some squared, वो जो हमने अभी लीनियर कॉम्बिनेशन निकाला है for the orthonormal basis, squared of that wave function with r1 prime comma, sorry, not r1, just prime, because we are writing, so r prime comma r double prime, this quantity, and this is basically uh, the squared. And similarly, we could have the probability that the other way around, that is, we would have one of the particle is at r prime and the other particle at r double prime, or we can exchange those particles with positions r1 and r prime and r double prime. Yeah. So then we could have r and r. So notice we have changed the positions. Yeah. So this is basically psi of r prime and r double prime ka whole square, and this is psi of r double prime and r prime ka whole square, or ka square. Yeah. Because and why we say, because we cannot tell which is which. Yeah. So this is because we cannot tell which is which is which. So we need to specify the probability for the both. Yeah. For the both ka matlab that one of the particle is at r prime and the other particle is at r double prime position, or the other way around, that one of the particle is at r double prime and the other particle is at r prime. And since we cannot say which particle is at position r prime and which particle is at r double prime, so the total probability that would be written in terms of these two, some of the squared wave functions. Yeah. And then we substitute the values of these wave functions. So what is in fact psi of r prime r double प्राइम का होल स्क्वायर, ये बराबर है किसके, दैट इज इक्वल्स टू the alpha square, the mod of alpha square. Then we have the mod of psi A. Psi A is basically the antisymmetric, and this is a function of r prime comma r double prime bracket close and mod square plus beta square, a mod of beta square psi of s, and then we have a function of r prime comma r double prime, and this is again a mod whole square. So this is the first term in this expression. So we are talking about, where is the cursor? So we are talking about this term, and we will talk about this term as well. So this was this term. Now the second term. Second term क्या हो जाएगी? Second term, in order to write second term, so let's write first the second term, wave function for the second term. And so the second term is, अभी हमने उसका mod square नहीं लिखा, so r double prime or r prime, and this can be written as um, alpha psi a of r double prime comma r prime plus beta, and beta of psi of s, which is symmetric by the way, and r double prime comma r prime. अच्छा, अगर मैं इसको इंटरचेंज कर दूंगा इन केस ऑफ एंटी सिमेट्रिक, इन केस ऑफ एंटी सिमेट्रिक अगर मैं इन दोनों को इंटरचेंज करूंगा, दैट इज आर प्राइम को आर डबल प्राइम से एंड आर डबल प्राइम को आर प्राइम से, तो यहाँ पर माइनस साइन आ जाएगा. सो इंटरचेंजिंग दीज टू would give me a minus sign in the first term, psi a, because it is antisymmetric. So if I interchange, so check here, I am changing prime from double prime. Yeah. प्लस दूसरे वाले में अगर मैं इंटरचेंज करूंगा कि सिंस द वेव फंक्शन इज सिमेट्रिक, सो अगर मैं इंटरचेंज करूंगा इन दोनों को, तो साइन विड नॉट चेंज एंड इट वुड बी बीटा psi of s, and this would be r prime comma r double prime. Yep. And now I would use the Cauchy identity, and from the Cauchy identity we would have, so now I take the mod of this quantity, so we would have r double prime comma r prime का mod square, and this would be equals to किसके बराबर, हम इसको स्क्वायर करेंगे तो this would be alpha square आ जाएगा. This would be psi a of r prime r double prime का mod square आ जाएगा, प्लस बीटा का mod square आ जाएगा, और psi of s of r prime comma r double prime का mod square आ जाएगा. ठीक है ना? And remember, we are using some Cauchy identity where you have a plus b whole square is less than or equals to mod of a square plus mod of b square plus 2 into something value, which but हम 2 into ab interaction नहीं लिख रहे. So we are saying less than or equals to. Yeah. So that's why, which is Cauchy identity. Yeah. And so the total probability, अब इन दोनों वैल्यूज को, यानी ये जो हमने निकाली हैं, इसको और इसको, इन दोनों को we would substitute in this equation, और अगर मैं substitute करूं, so we would have p of r prime, therefore substituting in the above, so we would have p of r prime comma r double prime would be equals to किसके बराबर, 2 times alpha square mod of psi of a antisymmetric r prime comma r double prime का whole square plus 2 times beta का whole square psi of s और r prime comma r double prime mod square. So this is basically the equation, the total probability जो आपके पास आ रही है. So मैं इसको बॉक्स कर दूं. So this is some boxed equation. Yeah, so this is some boxed equation. Yeah. Now, because the particles are in this, so we started our argument with by saying that the particles are indistinguishable. So since the particles are indistinguishable, any linear combination with any choice of alpha and beta, they would give you the same probability distribution. That is basically sort of a reminder from our lower classes. Okay? Since the particles are indistinguishable, so any linear combination would give you any choice of alpha and beta, and that any choice of alpha and beta should give you the same probability distribution जो हमने शुरू में बात की थी, याद है? हमने अभी इस आर्टिकल के भी शुरू में भी बात की थी कि there would not be any difference. So we started saying about the occupancy or the placement. So हमने कहा था कि अगर हम कोई दो या many physical states consider करें for placing those particles, then only those states are allowed which give you the same measurement or expectation value. And you know the probability density is basically an expectation value or the measurement value. So any linear combination with any choice of alpha and beta would give you the same probability distribution. We can't say which particle is in psi naught prime, though we cannot say which particle is in psi naught prime and which is in psi naught double prime, or equivalently, how much of psi A and how much of psi S to include. We can only say that the probability distribution is same. Yeah, so this is a very important consideration. So P should be independent of alpha and beta. अगर ऐसी बात है ना, any combination of alpha beta would give you the same probability, then इसका मकसद ये हो गया कि जो P है, जो probability अभी हमने ऊपर निकाली है, that would be independent of alpha and beta. The only way that can be true, वो सिर्फ और सिर्फ उस सूरत में हो सकता है कि probability of those two types of those two particles be in R prime or R double prime, at R prime and R double prime, वो सिर्फ और सिर्फ उस सूरत में हो सकता है जब आपके पास द एब्सोल्यूट वैल्यू ऑफ एंटीसिमेट्रिक स्टेट एंड द एब्सोल्यूट वैल्यू ऑफ ऑर्थोनॉर्मल सिमेट्रिक स्टेट वो कैसी हो, बराबर हो. सो दिस इज कैन ओनली बी ट्रू in this scenario only. Yeah, so we can say, because the particles are indistinguishable, meaning any linear combination with any choice, with any choice, any choice of, एक second, with any choice of alpha and beta should give the same probability distribution, the same probability distribution. मतलब, that is, we cannot say which particle is in psi naught, is in psi naught prime state, and which particle is in psi naught double prime state, or one could say, or equivalently, हाउ मच, बिकॉज ये जो अल्फा एंड बीटा ये किसको डिफाइन कर रहे हैं, वेट को डिफाइन कर रहे हैं. हाउ मच ऑफ साई ए इज कंट्रीब्यूटिंग एंड हाउ मच ऑफ साई एस इज कंट्रीब्यूटिंग. हाउ मच ऑफ psi A and how much of psi S to include or contributing. Yeah. So this is basically the argument uh, for uh, for the same probability distribution. So P should be, now इसका मकसद क्या हो गया? What is the outcome of this understanding? So P, the probability density. So P should be independent of अल्फा एंड बीटा. और ये किस सूरत में हो सकता है कि अगर ये किस सूरत में, द ओनली वे दिस कुड हैपन, द ओनली वे दैट कुड बी दैट could be could be true if psi a of r uh, r1 prime and r2 prime, mod of psi a of r1 prime is equals to psi s mod of psi s of r1 prime and r double prime. यानी दूसरे लफ्जों में, देर इज एन इक्वल प्रोबेबिलिटी फॉर दोज पार्टिकल्स टू बी इन सिमेट्रिक स्टेट एंड एंटी सिमेट्रिक स्टेट, विच इज समथिंग स्ट्रेंज, जो कि इसकी स्ट्रेंज बात अभी हम आइडेंटिफाई करते हैं. सो इसको मैं मार्क कर दूं, वेयर इज माय कर्सर. सो इसको मैं मार्क कर दूं 1 से. दैट इज, दिस इज द कंडीशन और कंस्ट्रेंट, या इसको हम कह सकते हैं इट इज अ कंस्ट्रेंट फॉर द सेम प्रोबेबिलिटी डिस्ट्रीब्यूशन कंडीशन आर्ग्यूमेंट जो भी हमने ऊपर लिखा है. और इस कंस्ट्रेंट को, दिस वुड बी सेटिस्फाइड इजीली अगर द पार्टिकल्स आर फार अपार्ट, है ना. अगर पार्टिकल्स बहुत दूर दूर हैं, तो दैट इज साइन नॉट प्राइम एंड साइन नॉट डबल प्राइम, ये दोनों एक दूसरे पर ओवरलैप नहीं करते वेव फंक्शन. तो देन दिस कंडीशन वन और दिस रिस्ट्रिक्शन और कंस्ट्रेंट जो हमने वन में लिखी है, इट कैन बी सेटिस्फाइड. बट एज टाइम प्रोसीड, क्या होगा? साइन नॉट प्राइम एंड साइन नॉट डबल प्राइम, they would the particles would come close to each other, and the wave function sin naught prime and sin naught double prime would overlap. And let's say we consider the case in which the point r prime is equals to r double prime. That is, they overlap such that the position of both these particles would be same. That is, r prime and r double prime बराबर हो जाए. तो उस सूरत में मॉड ऑफ साई ए ऑफ आर प्राइम एंड आर डबल प्राइम जो कि बराबर हो चुके हैं, वो सिफर हो जाएगा, बिकॉज एंटी सिमेट्रिक है ना, बीच में माइनस साइन है, तो वो तो सिफर हो जाएगा. जबकि दूसरे के केस में, सिमेट्रिक के केस में, वो सिफर नहीं होगा. और अगर सिफर नहीं यानी नॉन जीरो नहीं होगा, सो इसका मतलब हो गया कि जो हमने ऊपर बात लिखी है वो एक तरह का कॉन्ट्रडिक्शन हो गई, यानी वन जो है वो कॉन्ट्रडिक्शन हो गई, एक तरह का डायलेमा है, पैराडॉक्स बन गया. अब इस डायलेमा को हमें रिमूव करना है, और इस डायलेमा को रिमूव करने के लिए हमारे पास जो पॉस्टुलेट है, जिसको सिमेट्राइजेशन पॉस्टुलेट कहते हैं, वो इनफैक्ट वी वुड असाइन. या सो ये जो आर्ग्यूमेंट है, दिस दिस constraint that is equality 1 is satisfied if the particles are far apart. That is that is psi naught prime and psi naught double prime do not overlap. Yeah. But क्या होगा अगर हम time evolution, but as the time the time proceeds, uh, psi naught prime and psi naught double prime overlap. ठीक बात है. So let's say we consider a case. Consider the case where uh, case in which both particles in which consider in which rather both particles in which r1 prime, sorry, r prime is equals to r double prime. So r prime is equals to r double prime. Yeah. So इसका मतलब ये हो गया कि both points are equal. So उस केस में this would lead to psi a of r prime और r प्राइम दोनों सेम हो गए ना. तो ये किसके बराबर हो जाएगा? जीरो के बराबर हो जाएगा. बट psi of s of r prime और r प्राइम दिस वुड बी अंडर रूट टू. जमा करके देख लें तो यही आएगा. psi प्राइम, इसको मैं लिख लूँ और उसमें सब्स्टिट्यूट भी कर दें. सो r प्राइम and psi naught double prime which is r prime and this is basically not equals to zero. How is it possible कि ऊपर तो हम लिख रहे हैं कि ये दोनों बराबर हैं लेफ्ट हैंड साइड, यानी ये और ये बराबर हैं, लेकिन इस कंडीशन में जब ये ओवरलैप कर रहे हैं तो ये तो सिफर आ रहा है जबकि ये नॉन सिफर आ रहा है, नॉन जीरो आ रहा है. सो दिस इज सम apparent dilemma and we need to remove this dilemma. So this causes a dilemma. Yeah. Uh, so इसका मतलब है कि equation one cannot be satisfied. Yeah. I a I equation one cannot be satisfied. Cannot be satisfied. So this is basically something जो हमें प्रॉब्लम कर रही है. सो हम इसको कैसे रिमूव करें? But actually we made a small error. And what is that? P can be invariant if alpha is equals to 0 or beta is equals to 0, not in fact both are 0. जैसे ऊपर हमने लिखा है both alpha and beta are independent. So P can be 0. P हो सकता है सिफर. कब सिफर हो सकता है? और सॉरी, इनफैक्ट इनवेरिएंट हो सकता है जब या तो अल्फा सिफर हो या बीटा सिफर हो. मीनिंग अगर एक तरह के पार्टिकल्स हैं तो दे विल ऑलवेज बी इन वन